Hello everyone. In previous videos, I talked about how to download and customize MPLAB IDE, which is the program we'll be using to write our codes, as well as some notes about microcontrollers in general. And in this video, I'll talk about everything else you'll need to start your PIC microcontroller coding adventure. If you have no prior knowledge about microcontrollers or electronics in general, I suggest watching my previous video for suggestions, but it is optional. You can also check the description below to see the list of components needed from Advance. So, let's get started. You obviously need a computer and a programming environment to write your code on, which we already covered, but you also need three more things. One, obviously, is a microcontroller to program, and two, a programmer to put your code into that microcontroller, and three, some basic electronic parts and tools. Let's get started with the microcontroller. Even though you can use any microcontroller and follow along, you won't be able to copy my code or follow the same datasheet. I highly suggest getting the same microcontroller as mine. Throughout the series, I'll be using PIC 18F46K22. If you ever tried to look up a tutorial on PIC microcontrollers, you probably realize that most of them use PIC 16F877 or PIC 16F877A, which is the same microcontroller, but just a tiny bit better. I won't be using that microcontroller, and neither should you, ever. It's an ancient microcontroller, it's really slow, takes really long time to program, requires an external component to run, lacks many peripherals for its price, and is really expensive since it's so old. Now, 18F46K22 is not exactly new either, but it's not old. It's not so new that it's hard to get your hands on, but also not so old that it lacks speed, feature, or peripherals. It is really fast. Pretty much as fast as you can get with 8-bit microcontrollers. It has 4D connections, has all the basic peripherals, and is widely available, at least from my experience. It also has a couple of versions which are cheaper with fewer peripherals, so you can choose those if you feel that this microcontroller is overkill. This is the most advanced one of all the ones listed on the screen, but since I'll explain the peripherals one at a time, you can pick any of these microcontrollers as well. The datasheet covers all of them since none of the chips lack a peripheral that the others have, they just have less of them in count. Now I said that this chip has 4D connections, which I'll refer to as pins from this point on, but not all of the chips from the list have 4D pins as well. You can still get them if you want, but if you are an absolute beginner, I suggest getting one that also has 4D pins, so you don't have to look through the datasheet and find the exact pin out of your own chip. I actually just suggest getting the same chip as mine if you are an absolute beginner, to be honest. When you learn how to read and go through the datasheets of one microcontroller, you'll see that you can use any microcontroller out there, so don't worry about this microcontroller being bulky or expensive. After you learn, you can just choose any microcontroller you want for your given project. Another note, there are two main types of chips out there, surface mount and through-hole. Surface mounts are soldered on the surface of PCBs, while through-holes are put through their corresponding holes and soldered that way. By the way, PCB stands for printed circuit board. It's those usually green boards you see housing electronics. You'll see these terms referred to by their abbreviations, which is SMD for surface mount and DIP or THD for through-hole. SMD stands for surface mount device, DIP stands for dual inline packaging, and THD stands for through-hole technology. Why are there two abbreviations for through-hole, you might ask? For through-hole, DIP is used for chips like these, while THD is used for components like these. Kinda confusing, but DIP is the name of the packaging used for the chips, while THD is the name of the general technology that connects using holes through PCBs. So you can assume they mean the same thing for the most part, but DIP is a type of through-hole packaging. Which brings me to my point. Don't buy the microcontrollers that are SMD type. Buy ones that are DIP packaging. No product these days will use DIP packaging, since they are also just SMD chips that are put in a bigger, bulkier packaging using wires. Because of that, they are more expensive than their SMD counterparts, and way bulkier. But, because SMD packaging are so small, you can't exactly put them on a breadboard like we will be doing and prototyping and learn. So just buy a DIP packaging microcontroller. For the programmer, if you are a beginner, I just suggest getting PIC 3. There are many programmers out there, but I definitely suggest getting something official, so it supports wider range of microcontrollers and is configurable by the IDE. And most importantly, can directly start programming by pressing Program from the IDE. Trust me, you wouldn't want to generate a hex file every time and use a third-party program to load it every time you want to program. Also, please don't buy one of those cheap programmers that you have to remove and put your microcontroller into each time you want to program. But you also don't need to buy the newest and most expensive programmer either. Because we'll be using 8-bit microcontrollers, the newer programmers are just plain overkill. Personally, I'll be using a Picket 3 programmer in this series. For a beginner, I think Picket 3 is a good bang for your buck. Also, if you try to buy a Picket 3 right now, you'll immediately see that they are very cheap. That's because most of them out there are clones, since the official Picket 3 manual also has the schematic for it in the manual. Now, not all clones are the same. Not all may be able to debug or support the newer firmwares, or may just not work properly all around. I use a clone, since the prices are just insane in my country. And I can say that the clone I have here is great. It accepts all firmwares, can easily debug, can program pretty fast, and you get the idea. But I bought it from a local store, so I can't exactly recommend a certain seller. If you decide to buy a clone, it might just be a gamble, so do it at your own risk. For electronics, I'll construct a list of things to buy as I go along, so watch it all the way before buying anything. First thing you'll need is a power supply. You don't need to buy an exposed power supply though. What I recommend is to either get or buy an old phone charger. Also make sure that the charger uses a micro USB instead of USB Type-C, since USB Type-C chargers usually use protocols to determine its output voltage, which is what enables the fast charging feature, by the way. You can get it to work as well, but it would just be annoying for no reason, especially because they are more expensive anyways. In a previous video, I talked about how you can power your microcontroller using the programmer, but that is not recommended unless you are just programming that microcontroller. Only certain official programmers allow for this option, and even then, those programmers can only support so much power and are not designed to be used to power your whole circuit, especially if it has anything that draws more than a couple of tens of milliamps. Get your old phone charger, or any 5V USB charger for that matter. As you can see, this charger uses micro USB and was discarded, presumably after a phone upgrade. Don't worry about charger and cable being different colors. This cable was bought separately after the old one was damaged. Cut the end of the cable using a side cutter. If you don't have one, a plier or even scissors will do. After cutting the end, you need to strip the cable plastic. You can use a dedicated tool for that, like this. If you don't have one, you can use a knife to score the cable, then pull it to strip it too. After stripping the plastic, you might find shielding around the cables, if your cable was high quality, which looks like aluminum foil. Just cut it as well. After the wires are exposed, you might see 2 or 4 cables. If your power supply had its USB end hardwired, you'll likely see 2 cables. But if your power supply has a modular USB output, like mine, you'll likely see 4 cables, since the modular cables can also be connected for data transfer, which uses 2 extra wires along with 2 power wires. Usually the green and the white wires will carry data, while the red and the black wires will carry power, red being 5V and black being the ground. Since I know that the white and the green wires carry data on this cable, I'll just cut them off. But if you're not sure, you can leave them for the next part. Slightly strip the ends of the wires to expose the copper. Dedicated tools or pliers will help, but with some extra work and care, you can also do it with a knife. Now, you'll also need a multimeter, the quality of which doesn't really matter for our use cases, so it's up to you. You should check your wires even if they are color-coded. You wouldn't want to smoke your microcontroller after just buying it, right? Make sure your multimeter is in DC volts mode. Connect your power supply to mains and connect your USB cable to it, making sure that the ends are not touching. Most decent phone chargers will have resettable fuse inside of them, but you can never be sure. Connect the leads of your multimeter to the cables. Make sure your leads are connected the right way to your multimeter, meaning the black lead is connected to COM, which stands for common. Connect the multimeter leads to your power supply wires. If you see 5V, the wire connected to your red lead will be 5V and the other will be ground. And if you see minus 5V, the wire connected to the black lead will be 5V while the other will be ground. After making sure you got the power wires and noting their polarity, you need to be able to connect them to your breadboard. To connect different wires, you'll need to do a little bit of soldering. You'll need a solder and a soldering iron. For the solder, if you can, get something that has flux cores and is 0.5mm or less in diameter. You don't have to, but it will make soldering times and times easier, regardless of skill. For the soldering iron, you can get one of these cheap irons. They directly connect to the mains and don't have temperature control. You'll mostly see people saying to buy a soldering station instead, and I also recommend that, but if you are tight on money, these work fine for most of the applications. You'll also need jumper wires, either this kind or this kind. They are both fine as long as they can get into your breadboard. I'm using red and black cables since red cables are commonly used for DC power, while black cables are commonly used for ground. Cut one of the ends of both cables. Then strip their plastic a generous amount and expose their copper. Twist the coppers so the small strands don't separate. Do the same for the USB wires, after unplugging them of course. Strip their plastic a generous amount and twist their coppers. Align the jumper and USB wires as copper in an X shape. Hold one of the halves from the middle of the X shape and twist the coppers on the other half, wrapping the open one onto the other. Do the same to the other side. At the end, you should have a straight connection like this, which shouldn't separate unless you pull on it too much. Do the same operation on the black wire as well. Since the jumper wires are short, you can twist the whole cable to make it easier as well. After wrapping the coppers, we need to make sure that the connections are permanent and sturdy. Take your solder and soldering iron, in a controlled manner, dab and feed the solder in, while dragging the soldering iron along the copper. Make sure not to breathe in the fumes. It won't instantly kill you, but more than a little can be very dangerous. Only do this in a well-ventilated room, and if possible, use a fan to blow the fumes away from you. You don't need too much solder, you just need enough to cover the connection to make it permanent. Do the same on the other wire as well. You can't have the coppers exposed like this, so get shrinking tubes of the right size and fit them onto the exposed coppers. You can use electrical tape as well if you want, but this will look cleaner. Use a heat source, like a lighter, to heat up the tube, making sure to do it evenly and without burning anything. This is good enough, but to make it cleaner, you can use another bigger shrinking tube to cover and keep the cables together like this. You can shape the shrinking tube while it's still hot if it's looking twisted like mine. When they cool down, they will become hard and unshapeable. And there you have it, a USB power cable you can use to connect to your breadboard. Let's test it real quick. Here's a breadboard, and I'll just put 330 ohm resistor and an LED. Then connect the power cables to power the LED. And there you have it. Nice. Now, you have a microcontroller, a programmer, a power supply, a breadboard, the two resistors, an LED, and the optional capacitors. Now we can get to the first project part, so we can test if everything is working fine. First things first, insert your microcontroller into the breadboard. When your microcontroller is new, its pins probably won't be straight down like mine are. They will likely be too wide to fit the breadboard. You can bend them a little bit at a time by leaning and pressing them against the desk until they fit the breadboard. I've already used mine, so it fits nicely. Make sure this hole is in the top left, which marks the first pin, so we can directly reference the datasheet. We need to connect our microcontroller to the PC, but to connect our microcontroller to the PC, we need to connect it to the programmer first. The connection of Picket 3 are like this. The corresponding white arrow should also exist in the physical model, pointing at the pin 1. I'll use an extension cable like this, which should come with your programmer, since directly connecting the programmer would tilt the breadboard. The cables are completely parallel, so the connections still go with the same order. The top pin, meaning the first pin of the Picket 3, is MCLR. Connect it to the MCLR pin of your microcontroller, which is pin 1 for this microcontroller. This pin is used to reset the microcontroller, but it should also have VPP functionality, which is used to put the microcontroller into programming mode. The second pin is VDD, which refers to the positive voltage. It's 5 volts for us, so connect it to the positive voltage rail. The third pin is VSS, which refers to ground, so connect it to the ground rail. The fourth pin is PGD, which connects to the PGD pin of the microcontroller, which is pin 4D. The fifth pin is PGC, which connects to the PGC pin of the microcontroller, which is pin 39. The Picket 3 manual tells you to connect the resistor between MCLR and VDD pins with a value between 4.7 to 10 kiloohms. For this microcontroller, you don't have to do this. If you read the datasheet, this microcontroller already has an internal pull-up when the MCLR pin is active, so your programmers will work just fine either way. But I'll add it anyways, and so should you, in case you use a microcontroller that doesn't have this. It's a good habit to get into to save yourself the hassle in the future. The last pin is no connect, so just leave it as is. All the programmer connections are done, but we still need to power the microcontroller. This microcontroller has 2 VDD and 2 VSS pins. It's good to connect all of them if you can to give the microcontroller low impedance power. Pin 32 is the VDD pin, which is the 9th pin from the top right. I'll connect it to positive rail. The pin below it, which is pin 31, is VSS. I'll connect it to the ground rail. Pin 12 is VSS, which is the 9th pin from the bottom left. I'll connect it to the ground rail. The pin above it, which is pin 11, is VDD. I'll connect it to the positive rail. I'll also add the optional 0.1 microfarad capacitors between each of the power pairs to decouple the microcontroller. It should work fine without, but you should always decouple your chips. Next up is our LED. I'll arbitrarily connect it to the RD2 pin, which is the bottom rightmost pin. Make sure to connect the LED the right way. The longer lead should connect to the microcontroller's pin. Then, I'll connect 330 ohms resistor between the other lead of the LED and the ground rail. This resistor can be any value as long as it's above 220 ohms or so. Also, if it's more than 2 kilo ohms, the LED will be too dim as well. Now to power everything up. Connect your Picket 3 to your PC via the USB. By default, your programmer shouldn't supply power to the circuit unless configured otherwise, so it should be fine to power it up. Now connect your power supply to your rails as well. Make sure to connect it the right way so you don't fry the microcontroller. The first project will be blinking this LED, which is the equivalent of a Hello World project for a microcontroller. Blinking this LED will not only tell us that everything is working fine, but also by looking at its blinking speed, we'll be able to tell if the oscillator is configured correctly or not. Open up MPLAB X IDE. Now, from here on, I won't explain anything since I'll go step by step into all of it in the future. Again, I'm only showing this project for you to be able to test your equipment. So just copy what I'm doing. Right-click on the Projects tab on the left, and select New Project. Choose Standalone Project, and click Next. You don't need to select anything from the Family tab since its only purpose is to filter the Device tab below it. From the device list, find your microcontroller. Mine is PIC18F46K22, so I'll choose that. You can just type the name and it will automatically filter it for you, and that's why you don't have to bother picking a family above. If you connected your Picket 3 to your PC and your computer didn't fail to recognize it, along with no tool and simulator options, you should see the name of your Picket 3 followed by identifier numbers. Select it and press Next. From the compiler menu, select the XC8 compiler option, which is followed by its version and install location. Click Next. Give the project a name. It doesn't really matter, but I'll name mine First Example. Don't change anything else and click Finish. Now you should have a project tree on the Projects tab. I could put up a download for my project directly, but if the compiler gets updated in the future, or if you have a different version of my microcontroller, you may not be able to run it, so I'll discreetly put the files in the description. I'm going to put a link below for a .h and a .c file. After downloading, you can drag them directly to your project, but I suggest you make your own files and copy the code inside of them instead. From my experience, MPLAB doesn't handle removing and copy-pasting files too well sometimes. Usually a restart fixes it, but save yourself the hassle. On the Headers tab directory, right-click, go to New, and select Header.h option. Name it Config, and press Finish. Delete everything inside of it. Now, select Source Files directory, right-click, go to New, and select Main.c option. Name it Main, and press Finish. Delete everything inside again. The files you downloaded can be opened with anything since they only contain plain text. You can open them in Notepad or even in Chrome. You can just drag them to your Chrome's tab like this. Select all the code from the downloaded config.h and paste it to your project's config.h file. Do the same with the main.c file as well. Then press the Make and Program Device button at the top. If you did everything right, your microcontroller should be programmed and it should start blinking. It should blink for 1 second and turn off for 1 second on repeat. And this is the end of the video, and thank you for watching. If you liked the video, you can always leave a like and subscribe. It's always appreciated. And I'll see you in the next video.